And one other remark is if you you can turn the handle decomposition upside down. What we do is we replace f with minus f. This changes all the indices of the critical points. So remember we had I negative local coordinates minus xi squared, and then the rest were positive. Well, just changing the sign is going to interchange the positive and the negative eigenspaces of all the Hessians. So in particular, this turns index I critical points then interchanged with index m minus I. Critical points. And the corresponding result for handles, the I handles and the m minus I handles, switch over, so we're turning it upside down. So this is a useful trick in the proof of the H-cobordism theorem, amongst other things, where you can eliminate, say, all the 0 and 1 handles, then you turn it upside down, and you do the same to eliminate all the m and m minus 1 handles. I'll just say also, I'll advertise a set of notes of mine. So I'll end with an advert. Look at my notes on the proof of the H-cobordism theorem. For more details and a little bit more information maybe about handles and more so. I won't state it because I think you all know it. Okay, so that's all. Any questions?
Yeah. So this self-indexing assumption.
Mm-hmm.
Okay, so for instance, if I take the torus, can I see the self-indexing assumption? I'm just trying to simultaneously add those two one-handles.
So I think you've just got to think in terms of the kind of pictures I was doing before, where we had this, and then we were attaching like that. And you've got to think, well, what directions are you going to add at the same time? You need to choose, let's see, you need to choose some trajectories which go, here's the bottom, you need these to attach at the same time, and we also need something like from in here to come down and attach at the same time, and round the back. And these mustn't intersect the ones that are going up. So we need also to go up, say, here to the top, and maybe this will have to go through and miss this one. So how's that going to work? Yeah, I guess it just goes in through here and round like that. And then we have to have also these lines coming up and then round the back also. And then you play with that picture a little bit and fatten these lines up slightly. And that should give you the ascending cobordism, I suppose. You're decomposing it into two pieces which are the same, I think. Does this make sense? So, I'm not sure if I'll be able to draw this, but this is the idea. You need these not to intersect.
So maybe in this picture where it looks like a bulb.
This picture?
Yeah. So you can add the handle at the same time, then the second one.
Yeah. So you'll need a handle here, and you'll need another handle which goes up. This is sort of hard to picture. And this is now underneath in there. And then you'll need to attach simultaneously to.
No, that's it.
Yeah.
Then you go to the top. You cap it.
You get to the top and you cap it, right? Oh, okay, yeah. You just need to. You then run around all the boundary parts with the one circle and you cap off the whole thing.
Well, I was just trying to visualize the Morse function as sort of like
Morse function.
Yeah, sort of like sweeping elements like that
Yeah.
kind of way.
But was it, I mean, with its change, there was something about
Yeah.
self-indexing
Mm-hmm.
Morse functions of the I mean, that there is only one for every index there is only one. So for every I there is only one critical point. Is it possible?
Yeah, so there'll be only one critical value, but that will have lots of index I critical points in the pre-image, and this is the point you're simultaneously adding all of these handles, but you're putting them all together with the single value 1 in the real line.
Okay, then probably I need something else, because at some point
I mean, perhaps you want.
in this proof you probably choose a function, Morse function, where you move them away from each other. So you don't want to, or am I wrong? You don't want
Are you saying you want each
each
critical value to have a single critical point in the
something
pre-image?
like this. Is there something like that, or
Well,
is that
you just
making things up?
you just perturb all your critical values, your critical points slightly, just off this line, I suppose, and then you're just adding them in quick succession. But I'm not sure it's that important.
Yeah, probably not.
It will work either way.
So, but then what were we discussing? Then I didn't because I didn't.
We were discussing, so before we built up the torus by first attaching a one handle, then another one handle, and then a two handle, and we're saying, well, can we cook up a self-indexing Morse function on the torus so that you have your 0 handle first, then you add these together at the same time, because they both have the same value on the Morse function, and then you add on the two cell at the top.
So I guess what you were saying is it couldn't be a height function.
It's not a height function, no.
Yeah, you just gotta work it out with the gradient.
Well, I think you could embed this differently so that it was a height function.
That's what I'm thinking.
I don't really understand.
You don't think you can?
But I mean, you never have two critical points, and so why all this? Why do you want to attach two one handles at the same time? I mean, what?
The point is that you want, it's very useful to have I plus 1 handles attached only to I handles. So perhaps in the next talk I will talk about the handle chain complex. And so your boundary map will be given by these intersections of the attaching spheres with the belt spheres. And this is very clean if you just have I plus 1 handles attached to I handles, which you know you can do. And this is one way, sort of, from the Morse theory perspective, to see this. Okay.
Yeah, okay. I mean, it's just just a matter of what of perspective. You either attach. Well, I mean, you can attach one handle and then the other, but missing the. I mean, you don't attach towards.
Yeah.
To the one handle, but only to the 0 handle.
So before the problem was with the way you build it up. Usually, what you might have is you might actually have this one handle attached to this, and that you might have these trajectories that go up, going into. Okay, well, depends how you tilt your torus, but if it's vertical, I think you do have these then being the trajectories that go into
the
the
way
next
you
one.
drew your height function, the one handle attaches to the other one handle.
Yeah. Whereas if you tilt it slightly, I think you'll, well, as with these things, you can perturb it slightly and get a different decomposition.
Can I also ask, like, is there some kind of correspondence between things like belt spheres and, I don't know, ascending discs or something like this?
Not quite sure what you mean. I mean, the belt sphere is it's corresponding to all the, the plus these coordinates, which are going up. They're sort of, the function increases in these directions, so the trajectory is pointing up.
So if you had to take a section of like the height function or something like this, then that would correspond to something like ascending. So that is the belt sphere.
This is the belt sphere. I mean, the belt sphere was. So if we go back to this picture, it's these. It's going up, I guess. So. You end up with a picture like this, don't you? And the belt sphere is sort of these directions here out of this critical point. Not sure what else can be said.
Well, there's this, what was this thing? So when you were cancelling an I plus 1 with an I handle, that was if the belt sphere intersected. What was it?
So if you're attaching an I plus 1 to an I, then the attaching map for the I plus 1 has to intersect so the attaching sphere has to intersect the belt sphere of the I handle in just the one point.
So
we had pictures like this, yeah.
So maybe that's equivalent to this, like this, I don't know, this ascending disc or something like this, intersecting something in the I plus 1 handle above it in only one point.
To cancel. So these don't cancel, precisely for the fact that this is now attached to 2 points.
Yeah.
Right, you've got things coming down on both sides.
So if I call that downwards thing the descending disc.
Yeah, that's the descending disc from that point. Yeah.
Okay. And it hits it twice, so
it hits. Okay, so I see what you're saying. You say that this is the ascending disc from this point, and then you've got the descending disc from the point above, and you look at the intersections of those.
Yeah.
And you need that to be a single point if you want them to cancel.
Yeah. That might be a exercise.
Okay. Yeah, I didn't mention ascending or descending discs, but I've implicitly been talking about them. Okay. So we can discuss problems